Hello, everyone, and welcome to another wonderful day of physical chemistry. Today, we're going to pick up where we left off last time by talking about quantum tunneling. So, as we talked about last time, if I have a finite well, there is an actual probability that we can find the particle outside of the well. And again, one of the very important features is this happens even if the particle itself doesn't technically have enough energy to escape. As long as essentially the well potential is low enough and the wall is thin enough. So we're going to go ahead and dive in a little bit more to this idea of tunneling by establishing a barrier of height v and a width of w. And using this, what we can do is determine the potential of finding the particle outside of the box. But we're going to need to do this in kind of an unconventional way. We're going to have to actually establish three separate wave functions, and not just three separate wave functions, three different sets of wave functions. So the first is going to be for the case of, and for all of these, we're going to be focusing on the case where the particle itself doesn't have enough potential to classically escape. And so the first set of conditions is going to be inside of the actual box. So this is going to be to the left of the barrier because we're not going to really be focusing in on the size of the box this time, just more on the barrier itself. So the first is inside the box. And this is going to have our classic set of wave functions for a finite cell where we have forward movement, backward movement, and again, we can get at the constant in the exponential simply by knowing the energy of the particle itself. Now, then we come to a very interesting bit. So we have a particle going back and forth, again, imaginary components. Then something kind of weird ends up happening when we actually get to the wall itself. What we have is essentially no longer an eigenfunction of momentum. Instead, what we have is a slowly decaying exponential function. So this means that the probability of the particle moving through is going to decrease substantially with the width of the particle. And we're going to essentially model this using what I like to refer to as a damped exponential function. So we're going to have the major part here being the exponential or the wave function decreasing exponentially with this e to the minus k1x. Now, it is worth noting that your book uses a kappa. However, it turns out that kappa is really easy to confuse with k's. So I'm just giving it a k1 here. Now, the actual constant here is going to reference something kind of interesting. It's going to be how much higher, it's going to be related to how much higher the barrier is than the energy of the particle. So this means that if I have a barrier that's about the same height as the energy of the particle, well, then this is going to be a fairly small value, meaning that we're going to see a fairly low decrease in fairly low decay. However, if I have a very high barrier, this means I'm going to have a fairly large K1 value and then a very rapid decrease as I go into the barrier. Now, it is worth noting that this is going to be dampened by another exponential function with an increasing value, which is essentially going to help cancel out a portion of this decreasing value. And this can be considered as a way to kind of tailor the system with the value of C. And then we get to a really interesting case when we get to the right of the barrier. So to the left of the barrier, we have the particle moving forwards and backwards. And inside the barrier, we do have a little bit of forward and backwards movement. Now, something very interesting happens to the right of the barrier, because now there's nothing for the particle to bounce off. So as soon as it escapes the well, it's gone. And all we have is forward movement. And this is related by this e to the minus kx. So it is worth noting that this k is the same as the k on the first side. So this means that my particle has the same energy inside the box as outside the box, which means it has the same momentum as well. which is kind of a cool idea. So this means it's going to have the same wavelength, a lot of the same properties. But the biggest thing to note here is that we have a different prefactor. And this is going to be the part we're really focusing in on, because only a small proportion of the particle escapes. So we're going to find that this second prefactor, this A prime, is going to be much lower than essentially the value of how much of the particle is moving to the right originally. So we're going to have essentially a dampened release. And this is going to be part of the one of the things we're going to really focus in on is this ratio of A prime to A. So again, what we're going to find is that if we're going to use a lot of the same tricks we used for the one-dimensional particle in a box, because what we're going to do is use the fact that our wave function has to be continuous. And now that we don't have an infinite well, its first derivative needs to be continuous as well. And this is really what's going to help us determine what's honestly a lot of different unknowns, because we have 1, 2, 3, 4, 5 different constants that we have to figure out. And that's ignoring just the dependency on the energy and the potential of the particle itself. So what we know is that at the start of the barrier, when x is 0, all of our exponentials go to 1. So what we find is that a plus b has to equal c plus d. That's just going to be the case. So this means that we've got a continuous move from here to here. However, we also have the move at point W when we go from the wave function inside the wall to the wave function outside the box. And at this point, we're going to then just simply plug in W for our equation and set them equal to each other. And then again, don't forget that these Ks have a lot of embedded constants in them. But again, it's just the mass and potential and energy of the particle. But there's a lot in there. So this gives us 2 equations for our 5 unknowns. So we're going to need a couple more. So the next set of equations we're going to grab is using the first derivative. So what we're going to do is take the first derivative of the bound particle and the particle in the wall and set them equal to each other. Now note that we have a set of imaginary numbers linked up to a set of theoretically real numbers. Well, this gets a little interesting. Finally, we're going to do the same thing for the particle inside the wall and the particle outside the wall. So again, take the first derivative, set them equal to each other, get unlucky because now we no longer have 0, so the exponential hangs around. So this is a little unfortunate, as we now have 4 different equations for 5 unknowns. So we need something else to really kind of tie the system together. And as I said, one of the real big questions that we often ask ourselves is how much of the particle escaped. So what we can do is, instead of focusing on one of these given constants, what we can do is focus in on the ratio of a constant. We want to know the ratio of our A prime to A. But again, remember that these are the wave functions. We're going to be interested in probability densities. So what we're going to be focusing in on is the ratio of the squared prefactors. Again, note that when I'm talking squared, I am accounting for complex conjugates. So what we're going to focus in on is what's called the transmission probability, or essentially the probability of tunneling through the barrier, which can be given as the ratio of the squared amplitude of the particle escaping outside the box versus being located inside the box. Now, it's worth noting that this is just in terms of A prime and A. But this is our 5th equation, so we can take those other 4 equations on the previous slide, do a lot of really nasty algebra, and slap them together for a general equation for our transmission probability. Now we essentially have removed any sort of notation for the amplitudes, and all we're left with is an equation for the transmission probability in terms of the width of the barrier, as well as the energy of the particle and the height of the barrier. And using all of this, we can get at the actual likelihood of a particle escaping outside of a well. And again, one of the reasons why this is actually fairly important is it turns out we can hijack these same formulas for a scanning electron microscope, where I have essentially a particle from an emitter that goes to a conducting metal sheet, but has to go through a high potential barrier, notably air. And if you are able to essentially, and the idea of tunneling electron microscopy is that if I know the energy of my particle, and I know the height of my barrier, so essentially the difference in between the potential of the system where I've trapped it and the electron being trapped in air, I can go ahead and, if I know the probability that a particle made it through the air, I know the distance in between my emitter and my detector. And this is exactly how transition electron microscopy works, or tunneling electron microscopy works. You essentially run a probe over a surface and then watch the current go up and down, and that gives you the tunneling probability, and that gives you the width. This is tunneling in practice. However, we're often going to be a little bit more focused in on some special subcases of tunneling. So what we're going to be looking at is how the transmission probability is going to kind of be related to the ratio of the width, which is given here in these numbers. So 2 means a narrow well, 4 and 10 mean a longer well. And what we tend to find is that as the incident radiation goes up, we tend to see the ratio of the energy of the particle to the size of the barrier goes up. We tend to see a drastic increase in the transmission probability. And not too surprisingly, we see a much faster growth with a narrower well, because there's much less to get through. And not to forget, we have an exponential sort of drop off here. So by the time you have a fairly wide well, it's a little hard to go through. However, it is worth noting that by the time that the incident radiation is on par with the barrier, so the energy of my particle is on par with the depth of the barrier, we now actually have a fairly high probability of escaping. Usually not 1, but we approach that fairly rapidly by the time it's about 3 times. And it is worth noting that with a fairly narrow barrier, we got kind of the smooth function. But something very interesting happens when I have a thick barrier. And what we tend to find here is that we have a very oscillating behavior in between the energy and the barrier. And one way to think about this is what I need to do is make sure that my radiation, the wavelength of my particle, is in line with the width of the barrier. The more that I line up my wavelength, the easier it is going to be able to make it through the barrier. And so don't be too surprised if you sometimes see these odd oscillating behaviors, because like most things, it tends to come from quantum mechanical behavior. So something to watch out for there. However, let's go ahead and dive a little bit more kind of into this equation. So most of you know, my favorite trick is to kind of look at limiting circumstances to make sure it kind of makes sense. So first of all, if I have a very low energy, we would expect transmission to drop to 0, because again, you need to have some energy to go ahead and tunnel. We can kind of validate this out, because as the energy goes fairly low, what we tend to find is that this value starts to approach 0. So as this value approaches 0, this means this whole expression approaches infinity. We dominate the 1, but remember, we have an inverse relationship here. So we have 1 over infinity, transmission drops to 0. Woohoo! Then the next thing to note is that as our energy increases, we're going to see kind of the opposite behavior. As my potential energy gets much greater than my barrier, then what we tend to see is this value starts approaching infinity. This value starts approaching infinity, and then this whole value goes to 0, and then inverse of 1 is 1. So Higher energy goes, we asymptotically approach 1. Now, a really interesting case goes when we, instead of focusing on the potential, when we instead focus on this width part. So if I have a fairly large barrier, this means my W term gets kind of fairly large. So this means that as W goes large, this term will start to dominate and this term will die away because we have negative of width. So this guy's going to go to 0. This value is going to go large. And so then I have this exponential squared. But because this value is fairly large, we'd expect this term to dominate the 1. So we'll just drop the 1 here. Then what we tend to find is, well, this is negative 1, so let's go ahead and flip the whole equation. So my denominator now becomes a numerator, and my numerator now becomes the denominator, demonstrated by a negative 2k1, which again, as a reminder, is related to the ratio of incident radiation to potential barrier times the width. So again, as long as my barrier is sufficiently large, this expression will tend to dominate. And it's a kind of a fun way to look at our system. So this kind of gives us the rough idea of tunneling and transmission. And it is worth noting that tunneling is actually important in a lot of systems, and not just tunneling electron microscopy. As you may imagine, this tends to dominate among very light particles, which tend to have a little higher kinetic, which tend to have a little bit easier time moving through a system, because remember, heavy particles tend to stay trapped. So a classic example of a system where tunneling is very important is in biology, because it turns out a lot of enzymes rely on proton transfer. So moving a proton from one molecule to another. And it turns out that many of these barriers are very high but very narrow. And this height combined with its narrowness means that while you have proton transfers that might be classically forbidden, occur fairly rapidly, entirely based on the idea of proton tunneling. So tunneling, it's not just for electrons. So that brings us to the end of our finite wells and tunneling. Next time, we're going to be moving on to our good old friend, the harmonic oscillator, while things start to vibrate. Till then, take care.